All right. Well, thank you, Fernando and Pablo, for the introductions. My name is Andrew Thompson. I'm a PhD student at the University of Paris-Saclay. I was previously at the Institut Vedicom, as well as being an affiliate at Lawrence Berkeley National Labs. So I just want to thank everyone for taking time out of the day to join us with this webinar. I was looking at the chat screen. We have people from all over the world, so we're very excited about that. So just to go get right into it. So vehicle to everything, V2X energy services. It's a brief overview of what we'll be going over today. It's a brief introduction talking about where we are in terms of electric vehicles in the world today. Introduce this V2X energy services idea. We'll be talking a little bit about V2X and how it impacts battery degradation, which I know is always a hot topic when we're talking about V2X. And then we'll finish up with some regulatory issues surrounding V2X. So where are we now? So this is, every year the International Energy Agency publishes a very good report on the global EV outlook. This is the report for 2018. And as you can see, there has been a very large increase in uptake of electric vehicles over the last several years. And in 2017, we recently crossed the 3 million threshold in the world. You can see here. And this is almost an almost exponential increase of year on year end. And here we can see they're talking about BEVs, which is battery electric vehicles, and PHEVs, which is plug-in hybrid electric vehicles. So I just want to put out now is that when I refer to electric vehicles, when we're talking about V2X, we're referring only to battery electric or fully electric vehicles because of the capacity requirements for most of these services. So just to keep that in mind. So here on the bottom also, we see the relative percentage of electric vehicles, the electric car stock share to the overall light-duty passenger vehicles. And we can see that Norway actually has the largest share, which has crossed over 6% of the overall passenger cars have been electric vehicles, which has largely been policy-driven. So going on, various projections have been made. We have the IEA has made 2 projections based on the new policy scenario and the EV 30 at 30 scenario. The new policy scenario is a projection of electric vehicle uptake and growth based upon current and announced policies that nations have announced or already put into play, where the EV 30 at 30 scenario is based on the different countries' aspirations and the idea of getting a 30% market share for electric vehicles, buses, trucks, and light-duty vehicles as well by 2030. As we can see, that there's expected to be a very large growth of electric vehicle uptake, going anywhere from over 120 million vehicles to over 220 million vehicles by 2030. So it's expected that these very large growth trends will continue into the near future. Here's a bit about the growth in the electric vehicle charging stock, the charging infrastructure, which clearly is going to be an important issue as well. If we have a lot of vehicles, we're going to need to be able to charge them somehow. So here on the left, you can see the total increase in electric vehicle charger stock based on both publicly available fast chargers, publicly available slow chargers, private fast chargers, and private slow chargers. And you can see that the majority of the electrical infrastructure for electric vehicle charging has been dominated by private slow chargers. So this is typically chargers that people have installed in homes or businesses to provide charging services to their electric vehicles that they have. Whereas on the left, we have a breakdown of the public electric vehicle chargers. And we can see that with the electric vehicle stock here, worldwide, we've crossed the 3.1 million about, whereas 40% of that is located in China. 24% is in the United States, and the remaining, Europe and others, make up the rest of the electric vehicle stock. But when we look at where these publicly accessible chargers are, it paints a very different picture. For the fast chargers, China almost has 74% of the overall publicly available fast chargers. It dominates the rest. And this is largely due to the use of fast-speed chargers for electric buses. China has been heavily investing in that. Here's another graph on the global EV electricity consumption growth. And now we see again that China dwarfs the rest of the United States, all of Europe, all of Japan, and all others. And interestingly enough, we can see here, it's largely due to the two-wheelers. So in China, there's over 250 million electric two-wheelers, mostly small-ranged scooters and things along those like. And this is what has typically dominated the electricity consumption growth. And we can see in 2017, overall electricity consumption was over 50 terawatt hours. And try to put that in perspective, that's roughly about the energy demand of the country of Greece entirely. A majority of that was due to electric two-wheelers, and again, the majority of that is because of China, as we can see here. So what does this mean for the grid? So clearly, these electric vehicles will need to charge at certain times, and we have three example power profiles here of three different areas in the world. We can see in the dark green here on the top of each one. This is the electricity demand over a 24-hour period. And in the bottom, lighter green, this is the overall flow of traffic. Now note that these are both normalized to the overall power demand for the location and the traffic flow. It's trying to show the difference between the EV electric demand versus the overall electric demand for each area. We can see very characteristic shapes of this power demand, most importantly being that in each of the three areas, we have a peak towards the evening hours, which makes sense. Most people, they come home from work and they immediately plug in their electric vehicle to charge overnight. We can see it also here in Long Beach, California, and also here in the UK as well. And so why is this so important? So this is, I'm sure everyone has heard of at one point, the Duct Curve, the infamous Duct Curve. For those of you who don't know why it's called the Duct Curve, there's a very helpful drawing here to show where the duct comes from. And this is showing the California from CAISO, showing the impact of increasing solar penetration. So what happens to the net load over time is that due to solar noon, what cuts in during the middle of the day, solar production will generate more and more electricity, and it will cut into the overall demand curve, which forces this dip. But we see also the other impact of that is that increasing peaks in the evening, with not only a higher peak, but also a larger ramp towards the end. And this is a problem that's been well documented in many others, but we see, going back to the previous slide as well, is that electric vehicles, if left unmanaged, will add to this problem, add to this peak. So it's clear that electric vehicle charging, unmanaged, if left to their own devices, will add to this problem. So a bit of a summary of our introduction. We have over 300 million electric vehicles on the road today. 40% of these vehicles are located in China. We have a sustained nearly exponential growth is expected. Anywhere from 130 to 220 million electric vehicles are expected by 2030. And a significant portion of electricity demand increase is driven by this electric vehicle. And indeed, in several of more developed markets, This is the majority of the expected electricity demand growth coming from. And it's clear that EV charging, if left unmanaged, will worsen peak electricity demand. So the question is, what to be done? And this is where we believe that the V2X, vehicle to anything, energy services comes into play. So first of all, a bit of a definition. So when we're talking about V2X, what do we mean? So again, as already stated, the vehicle to everything, now V2X, is an umbrella term to explain the use of electric vehicle batteries to provide energy services and derive additional value from the battery asset during times of non-use. And so the designation of non-use is very important because clearly the primary goal, the primary usage of electric vehicle will be for mobility. So any time that we're talking about V2X is times of when the electric vehicle is not being used for the primary purpose of mobility, and also that these services need to be designed so that it does not impact this primary goal. So V2X services aim to generate revenue from the battery asset through dynamic or bidirectional charge control to provide benefits to the electric grid or to reduce, flatten, and shift peak energy consumption of buildings and homes. So what do we mean by dynamic charge control? So when we're talking about dynamic, we mean charging that is able to either anticipate and also respond to the active situation of the electric grid. And bidirectional charge control, which also encompasses unidirectional, is that not only are we talking about control that is based on current grid conditions, but also charging in one direction or charging and discharging based upon signals from the grid. This is what we mean by dynamic, and this is what we mean by bidirectional charge control. And so overall, V2X can be classified in the following operated modes. So we have V2G. This is what most people think about when we're talking about vehicle to V2X energy services. And when we're talking about V2G, we mean any time an electric vehicle is interacting with the grid. Usually, also, it's interacting with the wholesale market, as we'll see. Vehicle to building, V2B, refers to operating EV batteries to optimize building energy consumption. Usually this is either along with rooftop solar or other distributed energy resources. Vehicle to home, V2H, is very similar to V2B, but at a smaller scale, ideally for single customers, single homes, optimizing home energy consumption or using EVs as emergency backup power. And vehicle to load, V2L, any other instance of an EV battery providing energy to a load. Before, we used a nomenclature as even V2V, vehicle to vehicle, but we decided that it makes more sense to have less tedious nomenclature, to just designate anything other to vehicle to load. Now also note that we sometimes will see designations of V1G, or as known as smart charging. And this is where where electric vehicles can respond and change their charge rate based upon grid conditions. We're talking about only unidirectional, so only charging, not charging and then discharging back to the grid. Whereas V2G, we're referring to bidirectional charge control, both charging and discharging to the grid. So the V2X topology explained. This is showing ideals of how this would working, and we can see there's two key distinctions that can be made, is that V2X energy services that are acting in front of the grid, or in front of the meter, sorry, and behind the meter. And this is a key designation that we'll see going on. Whereas when we're talking about V2G, typically these resources will be acting in front of the meter. It's because it requires interaction with the grid, it requires interaction with the market as well, so all of these energy services will be provided in front of the meter. Whereas when we're talking about V2H, vehicle to home, or V2B, vehicle to building, all of these will happen behind the meter. And so there's less complexity involved with these two topologies. So this is Lazard's levelized cost of storage analysis is a very good report. They're on version 4 now. And so the idea for determining the economic argument for V2X is based upon what is the argument for battery stationary storage, predominantly for lithium-ion stationary storage technologies. And so here, Lazards has done a very good job of designated where these revenue streams can be derived in current markets today. And you can see there are 3 main distinctions. Revenues that are derived from the wholesale market, revenues that are derived from the electric utility, and revenues that are derived from the customer, either based on bill savings or based on backup power. And so likely V2X would operate in much the same way that stationary battery storage systems do. And so the idea for V2X identifying the value streams is probably operate a very similar way as battery stationary storage. So here we have a list of the different market products that V2X would likely be able to provide as well. So we have demand response at the wholesale level. We have energy arbitrage, which is buying power at expensive times and selling it, charging at expensive times and selling it later. Frequency regulation, which is typically a 4-second signal. I have an example later, we'll see. Resource adequacy, which is referring to the need to have capacity available at stress times. Spinning and non-spinning reserves. This is reserves that need to become online either in a short period of time or sustain the reserves over a long period of time. And also note that most of this nomenclature is a U.S.-centric terminology, whereas in other markets they have different definitions for these services, but they're still applicable in some cases. Whereas in the utility, we have distribution and transmission deferral, a value stream which derives its revenue from building capacity in locational specific areas so that there's less need to build out the transmission or the distribution system, less lines, as well as the demand response at the utility level. And whereas we're at the customer levels, bill management and backup power. And so another key point with this is that the use cases over here likely would require a stacked revenue stream approach. So that is to say, and this is the way that battery stationary storage systems are operated, is that they're not just providing one energy service over the year. You're providing several energy services. So for example, frequency regulation could be provided at the top most lucrative hours out of the year, but while being contracted for a resource adequacy contract, and then potentially also participating in the energy market as well through arbitrage. So the idea that all of the revenue is going to be derived from only one revenue source does not make sense. And indeed, it's not the way that thermal generators are operated today, nor is it the way that battery stationary storage is operated today. So this is the concept of V2X and the identified revenue streams of where they could participate. And so again, looking at Lazard's levelized cost of storage, this is for stationary storage systems, and they also looked at lithium technology, but also flow batteries as well. But only the top level of each one of these is relevant to what we're talking about here. So clearly, the main competitor for V2X will be battery stationary storage systems. And we can see that the levelized cost of storage is highly dependent on the usage. So you can see very large ranges depending on if we're operating in the wholesale market or if we're operating at a commercial level. We also see this distinction between services that happen in front of the meter and services that are derived from value provided behind the meter as well. So it's unclear still if V2X can offer a similar or better value proposition based on cost alone. While battery energy storage systems, stationary systems, have larger capacity and reduced complexity, think of a big battery sitting somewhere versus an aggregator who is trying to coordinate a fleet of electric vehicles. However, best, they suffer from very high capital costs, partly due to land siting requirements, balance of system costs, and etc. Whereas with V2X, in some use cases, there will be increased complexity, again, thinking about an aggregator operating a fleet of electric vehicles. However, there's a large reduction in capital cost. So as EVs, it's assumed the asset has already been purchased for the primary objective of mobility. What we're talking about now is marginal costs that are the most important. So not only the battery degradation costs, but the enabling tech that would allow an EV resource to participate and provide these services. And we will see later that V2X also can provide significant value to owners due to better battery management, which we'll talk about more in the battery degradation portion. So this is some results of some of the work that we did. This is a meta-analysis that looked at a variety of different resources that tries to determine what is the annual value ranges that can be derived from each of these revenue streams. And it's very clear immediately that there is a very wide range between them. This is due to the fact that there are very real locational realities to it. Not every resource will be profitable or highly profitable in every market. There are certain locational aspects, such as, for example, transmission or distribution congestion in certain areas. You have more profitable market conditions for certain revenue streams, etc. So it's very difficult to say that there is any one value stream that will be the saving grace. But there are some interesting trends that we can take from this. One being that resource adequacy is generally agreed is that is a very interesting and a very lucrative, potentially lucrative value stream that battery storage systems would be able to provide, and indeed V2X as well. Whereas bill management, transmission and distribution deferral, and frequency regulation also are interesting value streams. Now, it's also important to note that in the previous slide, when we were talking about costs, that was based on megawatt hour, whereas here, when we're talking about revenues, they're priced in dollars per kilowatt per year. And this is done to reflect the reality that for the behind-the-meter value, it's dependent on tariff rates as well, which are typically priced in dollars or cents per kilowatt. And one more key distinction, which I think will be crucial to the uptake of V2X, is the difference between power and capacity-based services and energy-based services. So we can see here in the wholesale designation, frequency regulation and resource adequacy really are power or capacity-based services, meaning that the underlying operation is not the energy that is being discharged, but it is either the capacity that is available at a certain time in the case of resource adequacy, or in the case of frequency regulation, it is your power rate. That is the underlying service that's being provided. Whereas with demand response or energy arbitrage, typically it requires a large amount of energy to be discharged. And we'll see when we're talking about battery degradation that high energy throughput services will be very detrimental to the battery and potentially cost prohibitive. So I also wanted to note that emergency backup power is actually listed in both power capacity and energy-based services because it will depend on the number of times that it's used throughout a year. If the emergency backup is only used for 1 hour out of a year, it will have a very different impact to the battery and a very different impact to the economics as well, rather than in the case where emergency backup is used very frequently. So this is the key distinction that we wanted to make when we're talking about V2X energy services. So to show an example of what we mean, this is a frequency regulation signal. This is a Reg D signal, it's called, taken from PJM, which is the largest wholesale market in the United States. We have here in the orange on the top the battery stationary signal response to the PJM regulation signal, which is in the blue. And you can see from the overlap, the battery storage system has almost instantaneous response time. Now the Reg D signal in the PJM market, D standing for distributed, it was designed for capacity-restrained, fast-acting resources. And indeed, it was designed and intended to be net energy zero, or as close to net energy zero over the time period. Now on the bottom, we can see the impact of a battery storage system following this regulation signal to the state of charge of that overall battery system. And so here, this is why I make this designation between power-based services, is that when we look at the state of charge swing, we have here at a baseline at 50% state of charge. Over a 12-hour period, we only have a maximum depth of discharge or maximum state of charge swing of only 10%, roughly. And so this constitutes a relatively shallow cycle, per se, but was able to provide a valuable service for the power and the flexibility, charge and discharge over a period of time. Here we're looking at another example, but this is now an actual vehicle providing frequency regulation. And we can see again in the blue signal being the actual regulation signal, where the vehicle power is in red, nearly overlays. So indeed, an electric vehicle service is able to follow a regulation signal reliably. But we can see here also is the impact of an imbalanced signal. We see in the beginning, the green is the impact to the vehicle state of charge on the battery. It's mostly charging during the first portion. But then, when the balance is mostly positive, the vehicle begins to discharge over time. And this is only for a 2-hour window. When we zoom out for a full 24-hour period, you can see that the electric vehicle is actually being charged for the majority of time that it's in the market. And it's only when there's a large imbalance in the signal where it gets discharged. So the balance of the frequency regulation signal is important. And it's very clearly could be a detriment or benefit. So you could say in situations where you have a positive net balance, is that you, while providing frequency regulation services, could be having a vehicle being paid to charge effectively. But the downside is if there's not a balanced signal, it could be very detrimental by having large changes in state of charge, which we'll see more in the battery degradation section. So here we have a pilot project that is actually going on at the LA Air Force Base. This is a electric vehicle resource that is actually bidding into the market. It consists of, I believe, 11 or 12 electric vehicles aggregated together and being offered to the local market as a virtual battery resource. I'm not able to share everything with this, unfortunately, but this gives you an idea of what an EV resource can be operated like. We see the overall energy available in the PV fleet, the upper and lower estimated capacity, and we can see here in the dotted lines is the actual upper and lower level of the bids that are then presented into the market. On the bottom here, we have the different bids that are submitted for both upwards regulation and downwards regulation throughout the time period. This is an example of one. So this is an ongoing project that has been going on since 2014. And we'll see that vehicles participating in the energy market now, providing frequency regulation services, has a daily regulation revenue of approximately 6.28 per electric vehicle, while only having a daily energy cost of about $1 per electric vehicle. Now for one day, it's an example, and it may not be representative of the future market prices. So to summarize, when we're talking about V2X, the operation highly depends on the topology employed, whether we're providing a service, a V2G service, or we're providing value with V2B, etc. Very likely, stacked revenue streams will be important, if not crucial, for the economics of V2X energy services, and with some key revenue streams being resource adequacy, frequency regulation, bill management, and transmission and distribution deferral. And also this key distinction between what are power-based energy services and energy-based energy services. And likely, V2G will be employed through aggregators bidding in markets on behalf of either a fleet of electric vehicles or on behalf of a pool of customers, whereas V2B would likely be, we will see realized in fleets of vehicles co-optimized with rooftop solar and distributed energy resources. Sometimes there's a lot of work talking about microgrids. This is what they mean. Whereas V2 Home, having a vehicle serve as a backup generator or being integrated with rooftop solar and the home energy system, and V2L, vehicle to load, likely to be used in either rural or emergency situations. So this is the overall framework of V2X. So inevitably, anytime I go to talk about V2X, everyone says, okay, economics, that's great. We have a lot of potential revenue to be gotten in the market or derived from the energy bill savings, but what is that going to do to the vehicle battery? It's a very valid question, and it's a very complicated question, and so unfortunately we don't have time. We could almost do an entire other webinar on battery degradation alone, but we will just get into some of the key points. So first, to understand a little bit about how batteries degrade over time. This is a result of my paper that is published in the Journal of Power Sources. And for those who are interested in more, I send you to the full paper. We can't get into everything here. This is a flow chart describing the degradation drivers and the impacts to the battery. So SOH, we're talking about battery state of health. And when we're talking about the state of health for a battery, we mean two things: the battery capacity and the internal resistance. Now, it's intuitive. We understand that the longer that we use batteries over time, the less amount of energy we can put into that battery. So that's intuitive. We understand the more you use your phone, the less charge it will hold. So that is a reduction in capacity, which happens over time. What may not be as intuitive is this internal increase in internal resistance. Over time as well, as the capacity is reducing, the internal resistance is increasing as well, simultaneously. And this is what's referred to sometimes as power fade, because more current needs to be extracted from the battery over time to be able to provide the same amount of power while still operating within the thermal limits. So you could, a way that we see this is that sometimes if you use your phone a lot over time, that it tends to get hot a lot quicker, and that's because of this internal resistance increase. So that's what we mean by state of health. Now, state of health is impacted by two concurrent aging behaviors: calendar aging and cycling aging. Now, calendar aging is the aging that occurs from a battery that is not in use. It's only due to the internal chemical reactions that are happening within the battery over time, whereas cycling aging is the aging that is induced on the battery through usage. So calendar aging is when there is a zero current, and cycling aging happens anytime there is a current going through the battery. And so what are the most important degradation drivers for both of these aging behaviors? And we see that there are several, most importantly being the temperature and the state of charge. And we actually see them in both temperature and state of charge in both calendar and in cycling aging. Highly important. And we see that situations that will have high amounts of temperature and high states of charge contribute to a number of degradation mechanisms. I won't get into detail of all the electrochemical degradation mechanisms and what they mean, but the key point to take away is that states of high temperature and high state of charge for a lithium-ion battery that is sitting is highly detrimental. Conversely, likewise, in the cycling aging, low states of temperature paired with high C rates. So what do we mean by C rate? For battery scientists, they use C rate as a normalized measurement of current. So a C rate is, for example, a current of 1 C is any given current that would discharge a given battery within 1 hour. So the current at which, with the battery capacity, that this battery would be discharged within 1 hour is referred to a 1 C rate. Whereas a current on the same battery that is discharged at 2 C would discharge that battery in 30 minutes. A C over 2 rate is the current that would discharge the battery in 2 hours. And so it is, C rate is current that is normalized to battery capacity. So we see the pairing of low temperature states with high C rate discharge induces a lot of wear and tear to the battery. In addition, high states of state of charge are detrimental, and also high depths of discharge, DOD, when we're talking about very large swings in state of charge, is highly detrimental to the battery. This is a very simplistic view of battery degradation. For interested readers, I refer them to papers. So here is another very good paper talking a very good visualization of what does this mean of calendar aging versus cycling aging to the battery. We have 4 instances in different temperature profiles with 10 degrees Celsius, 20 degrees, 34 degrees, and 40 degrees. And we can see in the blue, this is the overall battery aging impact due to amp hour throughput, so the energy that is extracted from the battery, dependent on the C rate, the charge rate, and it's showing us on the y-axis the induced capacity loss due to these 2 degradation drivers, they're called. So we see in the blue the overall life fade due to the battery, Whereas in the red, we have the impact due to cycling aging, and in the green, we have the impact due to calendar aging. And it's very difficult to visualize these two because clearly it's impossible to separate time from the battery as it's being cycled. And so you can see here that in normal or moderate temperature situations, the green dominates the overall life fade. And this leads us to a very counterintuitive conclusion that calendar aging, in fact, is the more important aging phenomenon. And we'll see why this is so important to understand. So this is some work. It's also another very good paper which showed how V2X can be used to minimize battery degradation. So this was done in a V2B topology. It's a simulation study based on an electrochemical lifetime aging model of the battery, which was employed with electric vehicles operating with a building, either discharging into an intermediary or discharging into the microgrid itself. And so what they were able to show is that due to the calendar aging importance, the calendar aging dominance in aging phenomenon, is that any charging strategy that could mitigate calendar aging could potentially prolong battery life while providing a valuable service of V2B. So we see here the overall capacity fade on the y-axis, which is given us a heat map here as well, red being worse, blue being best. And we see two different measurements, state of charge, that is discharge due to driving, and state of charge change that is due to V2G, but really it should be V2B here. And so what they found is that by minimizing calendar aging, and that in certain instances, say you come to your work, you discharge your battery to 70%, and you're sitting at 70% state of charge, and that in certain situations, by discharging an additional amount, you actually move yourself from a worse sitting state of charge to a better sitting state of charge that reduces the impact from calendar aging. And likewise as well, there's an impact as well to the internal resistance increase similarly as well. So again, don't have enough time to get into everything. I refer any interested parties to this paper as well. It's a very good resource. And so the results of this was that in certain situations, the V2G optimized charging strategy was able to greatly reduce the capacity fade and the power fade to the vehicles over time. There's another example of using V2G to minimize battery degradation. This is another simulation study that was done from the National Renewable Energy Laboratory. And what they found was a very interesting stacked charging strategy that was due to two concurrent requirements, both to minimize the state of charge that was sitting over time and also to minimize the overall power, which would cause raises in temperature as well. And they find this very characteristic charge strategy, which is very different from what is done normally. Normally what is done is upon charge-in, vehicles are charged at full power, and then they slowly trickle off over time, which charges the battery as fast as possible, but it's actually the worst way to operate the battery because it sits at a high state of charge for a long period of time. And because of the calendar aging dominance, this is the worst way of operating the battery. So these are a few examples of how V2X can be used to minimize battery degradation. And indeed, when comparing the V2X enabled charging strategy to the plug-in charging strategy, they're able to almost double the battery life in this simulation study. So in summary, V2X and battery degradation. The economic of V2X cannot ignore physical reality. So because of calendar aging dominance and battery degradation, economic valuations need to understand the degradation drivers, so that the temperature and the state of charge at which an electric vehicle sits is the most important component. Semi-empirical electrochemical battery models are our best estimation method, and V2X can be more valuable than the market revenue that is generated as additional value through battery life prolongation, through optimized charging algorithms that incorporate V2X. And another important note is that battery chemistry may in fact dictate cost effectiveness of the service provision. So this next section is going to be more generalized regulatory issues about when we look at markets for V2X, what are the questions that we're asking? So this is based on some work from our colleagues that develop a framework for looking at markets for participation of V2X with 3 distinct modules. First, do the rules allow aggregators to provide reserve? If they do not, it's clear that there's no possibility for V2X to enter into the market, so there's no need to, they're dead in the water effectively. Then the question is, do these rules allow aggregators to provide their full flexibility or only a limited provision of it? And the third is, do the rules allow aggregators to extract the full value of the service from the market? Now, as you probably imagine, there is no optimal market design for participants of aggregators at the moment. There is only various examples of them being close. So, Module A, what are the things we're talking about with market rules of aggregation? So the question of the technical definitions of aggregation. Who is allowed to aggregate? Are private businesses operating as aggregators allowed to get bid on behalf of fleets or of pools of electric vehicles? Or does the distribution system operator, the DSO, have to be the aggregator? So is there a preference to certain voltage connection points, the high voltage, medium voltage level? And if there are any performance requirements, so usually due to reliability and safety reasons. Another question is interoperability between DSOs. So if we have, if you imagine, a pool of electric vehicles, individuals, they're like, this is a moving resource, and where the electric vehicle is plugged in may not be always in the same place. And so having this interoperability between distribution system operators is important as well. So can aggregation happen between DSOs? And furthermore, what is the aggregation method? Are we talking about telemetry aggregation, so actual technical aggregation, whereas the aggregator is in charge not only of the coordination but also of the energy dispatch, or if there only is financial aggregation allowed, so that the energy in the end is dispatched by the DSO, distribution system operated? Module B, rules defining energy products. Some of the very important issues is the minimum bid size. So in several markets there is a minimum bid size that is required to provide energy services. It can range anywhere from 100 kilowatts to 5 megawatts. So for example, in PJM, it's now 100 kilowatts minimum to be able to bid in. So this is within the realm of possibility for V2X. Whereas in California, CAISO, it was 1 megawatt, and in other markets it's even as high as 5 megawatts. So this is a key consideration for V2X viability. Another important question is about the time duration. The amount of time the resource must be available. If it's over 4 hours, it's very unlikely that a capacity-restrained EV resource would be able to provide this service. And also, when is the distance to real-time reservation? I know in Germany, resources that are providing ancillary services need to be contracted 1 week ahead of time and need to provide a service for 1 week as well. And then this question of product symmetry. Is there a separation of upwards and downwards reserves? Are individual resources allowed to only offer upwards reserves or downwards reserves? which in the case of electric vehicle would be only charging or only discharging, and if there is a requirement to have a symmetrical offer. And finally, the Module C, rules for remuneration. So what are the payment schemes? If there are regulated tariffs, that small capacity resources are paid a generic tariff, as it's pay as bid, if it's uniform pricing, if it's mandatory versus voluntary bidding, meaning that if you are operating in the market, you have to bid and you have to offer your resources, versus voluntary, where you can bid only in the hours where you know it will be cost effective. And finally, if there are performance bonuses in the regulation. In PJM, for example, there's a certain performance bonus for fidelity and for also responsiveness as well. So these are important questions when talking about the regulatory issues when looking at markets for V2X. So, in conclusion, we have a significant portion of electricity demand increases driven by EVs. We expect anywhere from 130 to 220 million EVs on the road by 2030, and it's very clear that their charging must be managed. So to reiterate, vehicle to everything, V2X, is an umbrella term to explain the use of electric vehicle batteries to provide energy services and derive additional value from the battery asset during times of non-use. And there are several different new monetization opportunities of different services that could be provided, most notably resource adequacy, frequency regulation, etc. V2X can be used to improve battery lifetime. However, significant regulatory barriers still persist, and the current V2X economics is highly variable. There's a large locational dependency based on the market, based on the transmission and distribution congestion, and it's likely that stacked value streams will be required. So the question is how to realize this. Which value streams can be captured, and which value streams can be captured concurrently? These are some of the questions that will still need to be answered to allow for a widespread adoption of V2X services. So with that, I'll leave you the reference slides, and thank you all very much for attending.